All right, well, hey, welcome to week 2 of physics. Last time we kind of wrapped up all of the interesting sort of properties of light and started talking about reflections. And so we saw what happens with mirrors, specifically flat mirrors, and then curved mirrors. At least we looked at what happened if we followed the rays, just kind of followed them along and saw where images were. But we're going to formalize it today. We're actually going to get some equations that we can use so that we don't have to draw the pictures every time. And what's going to be beautiful about these equations is they're going to work for convex or concave or even flat mirror. And then after we're done with mirrors, we'll start talking about what happens when we have refraction. What happens to our images then, like when we were talking about how depths are weird, right? The apparent depth is different than the actual depth and things like that. So we'll talk about that with flat surfaces, and then we'll go to curved surfaces, which then brings up the idea of like lenses, why they do what they do. And all right, so we're going to still be doing geometric optics. It's just we're going to start moving away from just doing it geometrically, but creating formulas. But before I do that, I want to open it up to you guys about questions on any homeworks or anything, because I think the first set are due tonight, if I recall correctly. Anything we want to talk about? I just want to real quick ask Bradley, because we talked about that one. You asked me that one at the end of Diffie-Q's last time about the dispersion through the prism. Did that work out all right?
Yeah.
Yeah, okay, cool. Just a little bit trickier because those surfaces aren't parallel to each other. Wow, this might be a first. The first time that you guys have never had a question for me in physics. And I'm not saying, hey, yell out a question. I'm just impressed. All right, well, seeing you guys don't have anything to ask me about, then I'm just going to go ahead and keep talking about mirrors and the like. All right, so I'm going to go ahead and pause, and then we'll hop up at the whiteboard in just a second. All right, so last time we talked quite a bit about the geometric properties of reflection and how certain rays did certain things. I just want to remind you that the 4 really good rays to follow if you're going to use them for reflection. So we looked at the first one, those that were horizontal. So if you have a horizontal ray going out, remember the big thing about this is it reflects through the focus. So that's a really good one to start with. So like take the top of your image, run out horizontally, it hits the mirror and then reflects through the focus point. Similarly, you can use the one through the focus, because that one reflects horizontally. Right, so you go down through the focus, and then when it hits the curve, it comes out flat. Another really good one is to the center point. I don't want to call it the center point. How about the midpoint? Of the mirror. So if this is our mirror, I'm talking about the midpoint is right there. That's a really good one because it reflects at the same angle. Because that central line is normal. And so then the law of reflection brings that. And then the fourth good one is the one that goes through the center. So if we're talking about a curved mirror that's on a circular, if you go through the center of that circle, this one just reflects back on itself. So those are 4 really good rays. They're super easy to follow. And basically you only need 2 of them. You take 2 of them. If those rays bounce and come together, that's going to be a real image, and you're going to see that at that location. If they bounce and diverge from each other, if you backtrack them to where they come together, that's going to give you a virtual image, but that'd be the location of that virtual image. So those were the rays that we used geometrically. But like I said, I want to get away from that. I want to actually see if we can build a formula that relates all these different distances so that we don't have to draw the picture. Because, and that's a challenge. And if you're not really precise, it's hard to know exactly where things are. And we've seen that if we can do things numerically, that's usually better than trying to do it graphically. All right, so here's what we're going to do. We're going to do some geometry. And I'm going to go ahead and start with the mirror being a concave mirror. Okay, so we're going to have our concave mirror. You're going to see that what we derive here works just as well if it's convex, but it's going to be our concave mirror. We're going to have an image out here, or an object out here, I should say. And let's put some other features in here that we can reference. There's going to be a center of the circle. So let's designate that guy with a C. So in terms of some rays here, think about what we're going to get. If we take a couple of the rays, one, we could pass it through the center. It's going to reflect and then come right back. And then another ray that I want to use just to help us find the location of the image is the one that comes to this midline and then reflects off. That's that. So our image is going to be located with its head right here. So this image, is it real or virtual?
Virtual.
All right. So Victor says virtual.
No, it's real, right? Because it's.
Jacob's saying real. Ralph said real in the chat box. Okay, this one is real. Why is it real?
It's not behind the mirror. It's in front of it.
Okay, so it's not behind the mirror. It's in front of it. But it's also because those rays pass through where the image is located. Right? Think about the red and pink rays here. Those are actual light beams that are coming off of the object. And both of those rays pass through this point. So that makes it real. Okay, so this one, the way that we've got this drawn, this one's going to be a real image. But we're going to see that this formula works even if it's a virtual image from the geometry here. But we're going to go with this example. So let me label some things so that we can reference them later. I'm going to label this angle as theta, which means I know that this reflected angle is also theta. And then I'm going to label one more angle. I'm going to label this one right here as phi. All right. So now that we have all this, let's go ahead and start doing some geometry. So first of all, let's look at this guy theta. And let's look at the triangle that involves theta and the object itself. All right, so one more thing I'm going to do, because we haven't done this yet. I'm going to keep track of their heights. the heights of these arrows. And so the object, I'm going to say it's got a height of HO. And so then the image is going to have a height of HI. Okay, so we're going to do the same kind of notation that we did for distances. We had DO and DI. We'll have HO and HI. All right, so here's what we know. We know that the tangent of theta, if I look at this picture right here, it's the height of the object divided by this length right here, which is the distance that the object is from the mirror. And we called that DO before. So the tangent of theta is HO over DO. All right, now we can do another one with thetas. If we look at this triangle, that's the one that's formed from the reflection of the pink gray. But what I'm going to have to do with this guy is that's actually going to be the tangent of negative theta. Uh-oh. You okay with that? Do you see why it's why I'm going to use a negative theta there?
Because it's, you know, if you want to think of that as an axis, it's below it.
Yeah, I'm rotating it down. So I'm going in the opposite direction. So it'll be a negative. So that's going to be the tangent of negative theta. But similarly, that's going to equal HI over DI. Same idea, right? This side is HI, that's the height of our image. And then it's the distance away is the DI. All right, well, from our knowledge of tangent, tangent is an odd function, so that minus can actually be brought out front. So this would give me that the tangent of theta is equal to minus HI over DI. And now I can equate these two things. So what we get at this point is HO over DO is equal to minus HI over DI. Or alternatively, it's going to be a little bit easier if we look at it this way. All right. Now, we're not done, but I do want to put a box around this because this is an important fact. Because I want you to look at what those ratios are. The first one is a ratio of the heights. Right? HO and HI are the heights of the object and the image, respectively. So this is a measure of magnification. How big or small is that image we're going to see versus our original height? Well, that magnification actually also, it's going to be the same as the ratio of the distances for those things. Okay, so the closer that those two distances are to being the same, the less magnification you're going to get. And so real quick, just think about looking at your evil twin in the mirror. We already saw that that evil twin is the same distance behind the mirror as we are in front of it. So thinking about that and looking at this, DO and DI are the same, just opposite in signs because one's behind and one's in front of the mirror. So that's going to be -1, which tells us that the ratio of the heights should be 1. Your evil twin is the same size as you are in a flat mirror. So this even holds for flat mirrors. Turns out it doesn't have anything to do with the fact that this is a curvy mirror at all. But we're going to use this when we build another equation. All right, so far so good. Just a little simple, easy geometry, little trick. All right, now let's do the same thing with phi. So I'm going to make my tangent of phi. And phi's tangent is going to be HO over this length right here. The distance that our object is from the center. Well, if I want that length, I can take the entirety of the object distance and subtract off the distance to the center. So this is going to be DO minus R. All right, so that's the tangent of phi, at least in terms of those quantities. Now, there's another phi in this picture. You guys see where it is? I didn't draw one, but there is another angle phi somewhere in that picture.
Down the same line that the other phi is made by.
Yeah, this guy right here. Right, from our geometry, those things called vertical angles, I think. I don't remember the term for them, but
I can't remember either.
Whenever you have two lines that intersect, you know that angles on the opposite sides are the same. So that guy's still phi, but notice that it's rotating in the negative direction again. So we have to pull the same sort of trick. But if we do that, we're going to get the tangent of negative phi. And if we look at this one, the opposite side is HI. But now I need this length. And if I'm going to get that one, I have to subtract off the image distance from the radius. So this is R minus DI. So we're going to do exactly the same trick. Pull this minus sign out, set those things equal to each other. So we're going to get HO over DO minus R equals minus HI over R minus DI. And I can actually move things around so I get the same minus HO over HI. Now, this guy, I'm not going to box it because on its own, it's pretty useless. I mean, it still is a thing of magnification, and it's still saying that it depends on the distances, but also now the radius of the circle. Okay, it's not as useful by itself. But what we can do now is equate these two things. They're both equal to minus HO over HI. So we can equate those. And what we get is DO over DI equals DO minus R over R minus DI. And what's nice about this equation is that it's only in terms of the locations of the object in the image. I mean, yeah, it does have the radius, but it no longer involves the heights or anything. All we need to know are the distances. So I'm going to leave this part to you, but if you distribute, shift things around, group like terms, yada, 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 algebra, this turns into 1 over DO plus 1 over DI is equal to 2 over R. on that one you want a box. Because now we have a relationship between the two distances. And presumably you're going to know the radius of the mirror, right? That's going to be something that is known because you can measure that. You can determine what the curvature is. So you're going to know R. You should also be able to measure DO, right? There should never be an instance where you can't measure the distance from the object to the mirror. And what this is going to allow us to do is figure out DI. And DI, you can't always measure. In some circumstances, you could. Like this one, we could. Because we could have a screen that this image is projected onto. And then we can measure, where is that screen relative to the mirror, and that will get us a DI. But imagine that that image was virtual. There's no way you can measure that because it doesn't even exist. But now we've got a formula that's going to let us find it. Okay, so this is a biggie. This one's really, really big and is your friend. And in fact, it also works for flat mirrors. Like think about a flat mirror. What would the radius be if the mirror was flat?
Wouldn't it just be the distance?
So the radius of the mirror. Think about it, if as I'm getting flatter, what's happening to the radius of my mirror?
It's decreasing, right?
I think you want to go the other way with that. It's getting bigger, right? Like think about this. Think about the flat earthers. Why do people think that the earth is flat?
Because they don't know geometry.
Because they don't know geometry. But because the radius is so big on the earth that it appears that the earth is flat locally. Right? So as you flatten out, your radius is actually getting larger. And so if we're exactly flat, that's like having an infinite radius. So let me just write that. Flat is R equals infinity. And think about what happens to this equation if R is infinity. So we get 2 over infinity, which would be 0. So this becomes 1 over DO plus 1 over DI equals 2 over infinity, or 1 over DO plus 1 over DI equals 0. And it's not very hard to solve this for DI. And you see that DI is equal to negative DO. So the image location is the same distance away as the object's location. It just has the opposite sign, which means on the other side of the mirror. So even though we developed this with a curved mirror, it still also holds for a flat. So it turns out this is the one and only equation that you need for any kind of a mirror. If you know the curvature of the mirror, then you're going to know the relationship between the location of the object and the location of the image.
So it doesn't matter if the mirror is parabolic or hyperbolic?
Okay, well, it does. It does a little bit. But what you can say is that as long as it's circular locally, like small angles nearby, then this is what it's going to be. All right. But we did go with that it was a circular mirror. If it was parabolic, it has different reflective properties. And so it wouldn't quite hold. So technically, yes, this is only for circular mirrors or spherical mirrors, I guess, if you want to go to to 3-dimension. But if you can even approximate it locally as circular, which we can do most of the time, this will still work. All right, well, one more thing I want to add to this before we do an example, just so you can kind of see how this plays out. I don't know if you remember, but I mentioned the small angle approximation. And in terms of the mirror, it was this. If the angles are small, so meaning the angles that we're coming in with our light rays as they're bouncing off the mirror, if the angles are small, we saw that the radius was approximately equal to 2 times f, where f was the focal point. Excuse me. So the focal point was, again, where the parallel rays would bounce and come through. And so if you're sending in these rays at, so that there's not huge angles of reflection, they do tend to come at one point, the focal point. Well, if you substitute that 2f in here for r, the 2's cancel, and you get a slightly different formula. That looks like this: 1 over do plus 1 over di equals 1 over f. And so this one's useful if they give you a focal point. If they tell you, okay, all the light rays come together this distance away, you can just plug that guy in for f. And this is something that you can actually do in the lab. You could have a circular mirror. You could send in parallel rays. You can see where they all bounce and come together. And so you can easily measure your f, which is going to be simpler than trying to measure the r. But as long as those angles are small, this is a good approximation and it works out. All right, but really the one in pink is the better one because that does not require small angles. This always works. The one that I boxed in blue, that one only for small angles. So it's not quite as strong. It's real. Okay, so again, let me remind you about the sign conventions here. Because this is where people run into trouble. They end up using the wrong plus or minus signs. Okay, so these sign conventions, let me put here 4 mirrors, since that's what we're talking about right now. Okay, so let's start with DO. Right, it's going to be positive when in front, negative when behind. And this was one that I talked about where almost always your object's going to be in front of the mirror. The only way that's not going to happen is if the object for the mirror is actually the image of something else, and that image is sending it to be back behind the mirror. All right, so it's very rare that we're going to deal with that. So almost always it's going to be positive, but it's just in front of the mirror positive, behind the mirror negative. Okay, the DI. It's positive when real. and it's negative when virtual. So that's technically when we were deriving everything. I mean, that's how we built it. But I am going to put here because it helps out in this way too. Positive when it's real. Well, real images, these are going to show up in front of the mirror. And the virtual are going to be behind it. So it turns out that the practical usage for the DI is the same as with the DO. And you could actually say the same thing with the objects. A real object is one that has the light rays that pass through it. So it's real, right? So that's the positive. And then negative when it's virtual, which means the light rays do not go through it, which means it's not in front of them. All right, so then that leaves R and F. Well, for R, it's going to be positive when concave and negative when convex. Okay, so if we're dealing with a concave mirror like the one that when we built this on, that would be a positive R. If it was convex, if it was rotated the other way, then that's going to be negative. Well, check this out. This is beautiful. So if we think about R really has to do with where the center is, right? You know where the center is, and you can measure the R. Well, the way you know that it's positive, this is if the center is in front. And it's negative if the center is behind. Hopefully you're seeing a pattern here with the pluses and minuses. It's super awesome for mirrors. Because then the same thing happens with F. The focal length, it's going to be positive when in front. So if all the light comes together at a point in front of the mirror, and then it's negative when it's behind. So that'd be all the light is reflecting off and bouncing away, diverging, and you were to backtrack to the point behind. All right, so the thing about mirrors, positive if it's in front, negative if it's behind, period. So that with these formulas, whichever one, are going to be able to handle any kind of a reflection problem. All right, so let me show you one. Let's actually do an example of one so you can see how this plays out. And really, all we have to do is pay attention to our signs, our plus and minus. All right, so here's the deal. It's Christmas time. There's a Christmas tree up, and it's got nice silver spherical ornaments. And so you walk up to the tree, you are looking at your reflection in one of these ornaments, and you notice that, oh, this is clearly a mirror. It's a spherical mirror. I'm curious where my image is. I'm curious what my magnification looks like, and all that good stuff. All right, so let's see if we can do those calculations. So let me just give you some information here. So let's say that we suppose a 1.6 meter tall person is standing 0.75 meters away from a spherical ornament. Okay, so 1.6 meters, kind of average height for a man, and 0.75 meters away. All right, now, if you think about it, I need to tell you a little bit more information. Because right now, what have I given you?
H naught and D naught.
Okay, so we got H naught and D naught. Now, if we want to do anything with this, we need to know something about either I, so DI or HI, or we need to know the radius, right? So we need to have one more piece of information. So how about I tell you the radius? Okay, but I'm going to be mean. I'm going to tell you the diameter. Okay, so the diameter of the ornament, I ran numbers. I want to make sure I use the same numbers here. Is 7.27 meters. Okay, so I have two questions for you. The first is, where is the image located? The second question is, how tall is the image? And I'm also going to guess this is, I'll call that 2A because there's going to be a 2B. What is the orientation? All right, so basically I want to know is, where does it look like your little evil twin is? How tall is your evil twin? And is your evil twin standing upright or upside down? All right, so you now have enough information to answer all of these questions. So first things first, let's just label all the information that we have. And everything is in all kinds of weird units, so we should probably make it so that they're all the same. You good with meters? Was good, tried and true. Okay, so here's what we know. We know HO is 1.6 meters. We know DO is 0.75 meters. And we know R, we have to cut that in half. So the diameter is 7.2 centimeters. The radius is 3.6 centimeters. So that's going to be 0.036 meters. But let's think about pluses and minuses here. So the object, since it's a real object, since it's a person in front, we know that HO and DO are positive. What about R? Is R positive or negative?
It's negative.
All right, so Bradley says negative. What do the rest of you guys think?
Yeah, negative.
So think about, where's the center of that sphere? The center of the sphere is inside of the ornament, which is behind the mirrored surface. So it is going to be a negative R. All right. So now with this, let's go get what we need. So where is the image? That means we need a DI. How tall is the image? That's going to be an HI. And then the orientation, well, we'll see if we can figure that out from the information. Okay, so let's start by getting DI. So we're just going to use the formula that we've got up here. It's still surrounded there in pink. But let's put in our numbers that we have. So we've got 1 over 0.75 plus 1 over DI is equal to 2 over negative 0.036. All right, well, that's enough for us to go ahead and calculate for DI. And we get DI equals negative 0.0176 meters. All right, so where is that?
Inside the sphere?
Okay, it's inside the sphere, so it's behind the surface. So it's going to appear to you, if you're the person standing here looking at that ornament, it's going to appear as if your evil twin is on the other side of the mirror, meaning inside the sphere, right? So where is the image? I'm going to write 1.76 centimeters behind the mirror. Okay, so this is just like when you're looking at a regular old mirror, right? When you're in the bathroom brushing your teeth. Same deal. It looks like you're behind the mirror. Well, that's what it's going to look like here. It's going to look like you're on the other side. You're inside the sphere. All right, so now question 2, part A. How tall is the image? All right, well, that means we want to find HI. So let's go to the formula. This was like the first one that I boxed a while ago. And that was that we had minus HO over HI is equal to DO over DI. So if I solve that for HI, that's going to equal minus HO times DI over DO. So let's put in our numbers. So HO was 1.6 meters. DI, we just calculated that, was a minus 0.0176 meters. And then DO, we knew that we were 75 centimeters in front of it. All right, so we run the numbers on that, and we get 0.0375. And notice that the units are going to be meters because all of these things were in meters. So one of the meters cancels with the other, so dimensions work out. Okay, so how tall is the image? Well, it's 3.75 centimeters. So your evil twin is a super teeny tiny evil twin. Right? You are 1.6 meters tall, and this thing's only a couple of centimeters tall. But if you've ever had this experience, and I imagine a lot of you probably have, you've seen yourself in reflections like this. Yeah, you're very small. Okay, so then the last question is, what is the orientation of the image? All right, so what do you guys think? Is this thing going to be upright or is it going to be flipped over?
Upright.
So Bradley, you say upright. Why?
It's convex surface.
All right, so you think we're always going to be upright in a convex surface?
Maybe not always, but a lot of the time.
All right. So your hunch is upright. Well, you know, physicists don't like hunches. We want answers. Turns out we can know what the answer is to that by what we just calculated. And it all comes to signs. Look at what we got for HI. HI was positive, which means positive height means upright. Right? And in fact, that's the one thing that I didn't talk about with sign convention, because it doesn't really have anything to do with mirrors per se. But if we're going to go that, like, think about how we started. We started with our HO was a positive 1.6. I'm already defining positive means upright. So if our answer for the other height is also positive, that means it's upright as well. So this one's not flipped over. It's going to look like your evil twin is standing in the same orientation as you, just much smaller. All right, so here's your typical spherical mirror kind of problem, and they're all the same. The only thing that changes is concave versus convex. Okay, so your R is positive versus negative, or maybe you've got an image that's now upside down, or negative, that kind of thing. So just realize that it's just a matter of keeping track and plugging stuff in. That's why I'm a huge fan of writing down everything they tell us. And I take care of the signs right away. So I don't have to worry about that later, because that's where mistakes are going to happen. So the one other thing I just want to mention before we get to what happens when we go through refraction is that there is another number that you'll often see associated with this, and that is magnification. And the magnification is defined as the ratio of HO over HI. And so sometimes that's what they'll tell you. They'll tell you, okay, this mirror has a magnification of, insert number here. But that's enough actually to solve these things and figure out what you need. Because remember also from that formula, if I solve it for the HO over HI, it's negative DO over DI. So if you know what the magnification is, you can actually use that to find your image location given your object location.
and so on. All right, so I want to go back to something Bradley said when I asked if this was upright. And he said yes. And I said, why? Well, because it's convex. And I said, are convex images always upright? We now know the answer to that. Because if it's also upright, that means your magnification is positive. Right? It's got the same orientation, so this ratio is going to be positive. Well, if this is positive, that means the ratio of the locations has to be negative. All right, well, if we're talking about one that's convex, if your image is behind, then it's going to be upright. If your image is in front, it's going to be upside down. Right? And so in terms of is it always true for convex or always true for concave? It turns out that it matters a little bit, the location of your object relative to other things. Like a great example is a spoon. Have you ever looked at your reflection in a spoon? If you haven't, it's something you can do after class, or if it's handy, run to the kitchen and grab a spoon. And look at your reflection and the bowl part of the spoon, right? The concave part. And move it towards you or away from you. And what you're going to see is that your reflection flips. Sometimes it's upright, sometimes it's upside down. Because of that formula, it matters where you are relative to the radius of curvature. But anyway, basically the idea is if it's a virtual image, so we got a real object, virtual image is always going to be upright. Real images are always going to be upside down. Always, when we got a spherical mirror. All right, so how are we feeling about mirrors? Cool with it? Think you can do these problems when you run into them now?
I don't quite understand the whole distinction between virtual and real images.
Okay.
Because I mean, if I think about it, aren't all images that we see, virtual, considering it's all, happening in our brain?
Okay. But this is where we need to get away from outside world definition of real and virtual.
Okay.
We go to physics world definition. Physics world real, and this is object image, doesn't matter. Real means the light rays pass through that thing. So for the object, the light rays are coming from that object. For the image, the light rays are passing through it. Virtual just means that the light rays appear to be passing through it, appear to be coming from it. So think back to the picture that I drew when we developed the equations, right? And we had there was the one light ray. Well, here was our arrow. The one light ray came and bounced off. The other one went through the center and bounced off. And of course, we're looking for where they meet. But this thing is real because the light rays actually pass through it. If it was virtual, let's just do the looking at ourselves in the ornament thing real quick. Right, follow the rays here. There's going to be the one that goes through the center and then bounces back. And then maybe another good one would be, let's take that one, right? That's coming to the midline and bounces off. Now notice that those two rays don't come together. I mean, they came together at where our object was, but they don't come together otherwise. So what we would have to do is backtrack them. And so they don't come together, but they appear to come together back over here. So that's why this one's virtual. There are no light rays that actually pass through that, because all the light rays are getting bounced off the mirror. So that's why we'd say that it's virtual, because it just appears to our mind, because we're trying to take those rays and interpret where they're coming from. They're going to appear that they're coming from back behind, and therefore it's a virtual image. Does that make sense?
Yes.
Okay. So real light rays are going there. Virtual, no, there are no light rays there. It just looks like it. All right, so there's reflection. And it turns out it comes down to really one equation. I mean, I guess then there's the second one with the magnification, but really it's the 1 over dO plus 1 over di equals 2 over r. That's all you ever need to do anything with reflection. All right, let's take a real quick break here. And when we come back, we'll talk about images due to refraction. All right. Okay, so now we see how mirrors work. Super easy. So the next question is, what happens when we have refraction? Instead of reflection, what about refraction? All right, so we're going to start exactly the same way. We're going to start with, what if we got a flat surface? Then we'll turn our attention to, what if we've got a curved surface, and kind of go from there. All right, so let's look at refraction. All right. So let's just start with the picture that we've always started with. We're going to have a flat surface here, and we're going to have light that refracts. All right. Actually, let's do this vertical. Let's do it the other way, because I think it's going to make more sense when we think about it this way. Let's think about an image underwater, okay, or an object underwater. So let's say this is the lake. So we're out on the lake, right? You're just hanging out on your kayak with Larry, drinking some cold root beers with him, having a wild old time. Can you imagine Larry drinking root beers? I have seen it happen, believe it or not. All right, so let's say we've got an object down under the water. So maybe we see, a rock or something that we think is kind of interesting. So here is our object, and let's just go with this depth. We'll call it HO. Okay, so it's not the height of the object, but it's the location of the object. All right, now think about rays that are coming off of that. They're going to be coming up here. And let's just draw a couple of them. So like there's one, and there's another. And both of those are going to refract. Now, if this is, we got N1 and N2 here, Like if this was air and water, we're going to go with that N1 is less than N2 for this picture. Right? Like air and water, or it could be water on glass or glass on diamond or whatever, but let's just go with this. All right, so what's going to happen when they bend? Are they going to bend further away from perpendicular or closer to perpendicular? Is theta going to get bigger or smaller?
We're looking at it from outside the water, correct?
Yeah, the light rays are going from N2 to N1. So they're going from bigger N to smaller N. So what does Snell's law says? What does Snell's law say about the angle then?
It's going to be larger.
Okay, it's got to be a larger angle, and those angles are relative to perpendicular, right? So it has to be bigger away from perpendicular. So that means that these things are going to bend so that they go more away from perpendicular. So there's that one, and then let's just say that that's the other one. All right, so cool so far. So in terms of how far they're going to bend, depends upon N1 and N2, and then also what that original angle was. But regardless, it's going to do something like this. Now, notice that those rays are still diverging. So if we backtrack those, so if we just follow those backward, this is what our eye would imagine that those rays are coming from. So to our eye, it would look like that object is located up here at the pink dot instead of down at this kind of maroon dot. Okay, so there's definitely a different apparent depth. So I'm going to call that HI. And so the question is, what is that HI? All right, well, firstly, that's a super hard question to answer because it depends on the angles. These two are coming with fairly small angles, right, compared to theta. But what if those two were coming, or to the perpendicular, but suppose those two rays were coming like way over here. We're going to get very different things depending upon those thetas. So what we're going to do is we're going to say, we're going to do basically our good old small angle approximation as always. We're going to assume that the thetas are small. So what that means is that when we're looking down, our eye is mostly above the object that we're looking at. Okay, so if this is, we're out there on the lake and we're in our kayak, root beer in hand, we're looking at things that are mostly below the kayak. We're not looking at things that are over there, not looking at things over there, looking at things mostly below us. Okay, so that's the first thing that makes this complicated, is that it totally depends on what your theta is. So we're going to go with small angles. So if we do that, if we say that the angles are small, so that we're looking down mostly from right above, it turns out that it's a really easy formula. And what we get is that apparent depth, HI, it's going to equal N2 over N1 times HO. Hold on, I think I got that backwards. Because we should have smaller HO. N1 was smaller than N2. Yeah, these are upside down. Okay, so this is how you can figure out what the height of the image is relative to these guys. Right, so just realize that when I set this up, I'm saying N1 is where we're, oh, you know what? I want to do this. And I apologize. I'm actually going to call these N1 and N2, where N1 is in the water, is the water, and N2 is the air. Just so that we're kind of standard with the one subscript, meaning where we're starting, right? Like whenever we use Snell's law, we always go with one is where we're starting. So in this case, N1 is greater than N2. And then that way my formula will be what I wanted. All right, so I apologize for that. I'm trying to be consistent with the book. And you know that's not my strength. I like to just do things how I do them. All right, well anyway, so if you assume thetas are small, you get this. And let me show you where it comes from. It really does come from Snell's law. If you look at just one of these, all right, so let's just look at one of the two rays. We'll look at maybe the first one. So if we have this happen, where this is the water surface. Right, let me exaggerate it a bit more like we had before. Well, not that much. So think about Snell's law with our perpendicular here. If this is theta 1 and this is theta 2, we get that N1 sine theta 1 is equal to N2 sine of theta 2. All right. The other thing that we're going to do is let's backtrack to our image. So let's just say that the image is right here. So on this little triangle, that guy's HO. And similarly, we've got on the bigger picture, this distance is, sorry, that's HI, height of the image. The image is HO. All right. Look at these triangles though. Like this one. I know that this is HO. I don't know what this length is, so I'm just going to call it X. But what I've got is that the tangent of theta 1 is equal to X over HO. All right, well, if you do kind of the same thing, but you look at not that red triangle, but this red triangle, notice that up in this corner, that's theta 2. So you can do the same thing and you get tangent of theta 2 that's going to equal x over h1, or sorry, hi. So you can put those two together, and that gives you, if you solve both of them for x, we get HO tangent of theta 1 equals HI tangent of theta 2. Okay, so we had Snell's law right here. And then we have this other one that just comes from the geometry. But this is where we use the small angle approximation. If the angles are small, sine of theta looks like theta. Also, tangent of theta looks like theta. Okay, so that's the small angle approximation. Hopefully you guys are okay with that. We use it all the time in physics. And it comes from like basically the limit laws in math. Like if you remember the limit as x goes to 0, sine x over x equals 1. That basically just tells you that the angle ends up being the same as the sine when you get very small. All right, well, because of that, this equation becomes HO theta 1 equals HI theta 2. This one becomes N1 theta 1 equals N2 theta 2. So we can actually put that together to get rid of the theta 1s and theta 2s, right? Like if we do the same kind of trick we did with the images from reflection. You're going to get HO over HI equals N1 over N2. If you just solve it for a ratio of theta 2 over theta 1. And it takes one more step to bring us to this. All right, so let's put a box around this one. And so this is, like we talked about before, this is why it looks like things in the water are closer to you than they actually are. Right? If you were to put in the ends for air and water, air is 1, water is 1.33, it's around 4/3. So 1 over 4/3 is 3/4. So it looks like things are 3/4 of the depth they actually are when you're looking at something in water. So if something is really 4 meters down, it only looks like it's 3 meters down. It looks much closer to you. All right. So we had talked about this fact when we talked about refraction, but now we can see exactly where it's coming from. We can see why it plays out mathematically, and we now know exactly how that image location is going to compare to our object location. So when you've got a flat surface, this is the formula. This is exactly it. But notice that the object and image are both on the same, in the same area, right? They're on the same side of this refractive surface. And think about this guy right here, the image. Is that a real or virtual image?
It's virtual, right?
It is virtual because the light rays don't come from it. I mean, look, we had to backtrack in pink, right? The blue rays themselves are not coming from there. So it's a real object and a virtual image. Okay, so there's your flat surface. And that's what's going on. But we had to make use of that small angle approximation. If we don't make this assumption, oh my God, this is a horrible thing to try to solve. Right? You look at that system, now we're going to have ratios of tangents and sines and, okay, well, we can use some trig to simplify it a bit, but it's not nice. It's not neat. It's not quick and easy. So this does require small thetas. So it does not apply to, I'm looking at things far away from me. This only applies to, I'm looking at things that are mostly directly below me. All right, so there's your flat surface. But flat surfaces are boring. And in fact, most surfaces we see are not flat. And if all we ever had were flat surfaces, we wouldn't have lovely things like corrective lenses. I mean, your eyes wouldn't even work. They work the way they work, right? We need to have these things that are curved. And so let's look at what happens when we have curved surfaces. So with the curved surfaces, the geometry is going to be a bit more complicated. Right, this one was easy. I made a couple of right triangles and then I did the small angle approximation and everything was good. This one's going to require a little bit more, but let's go with, here's our curved surface. And just imagine that this is, you know, definitely deep enough of a surface that we're going to see what we need to see. So this wouldn't exactly be like the lenses of my glasses, because the lenses of my glasses are thin, right? They're going to end here pretty small. But this would be, imagine just like a tube of glass with a curved surface on top, right? Something like that. So this is what we're going to have. Let me put on my midline. And let's put an object out here. So we're just going to look at a point again. So we're just going to have this orange point as our object. And what I want to do is I want to look and see, where does it appear to be located? So we're just going to take a ray off of this and we're going to follow it. So there's going to be a ray, comes up here and hits the glass. Let me go a little bit higher. I think it will help us when we need to reference things and do the geometry. All right, so let's think about what happens. There's going to be a perpendicular. That perpendicular, if we backtrack it out here, that's going to show up at the center of the circle, or the center of the center of the circle that forms that curvature. Okay, so that guy's going to be C. All right, now it is going to bend. Let's say, again, we've got N1 out here and N2 on the inside. All right, so we're starting at 1 and we're going to 2. And let's go with that N2 is bigger than N1. So we're going from air to glass, air to ice, something like that. Okay, so if we go to bigger N, that means we need a smaller angle. So it has to bend towards the perpendicular. So it's going to do something like that. Again, I need a little more space. Hold on. That still looks like it bends towards. All right, so here's everything. So let's start labeling stuff. So this angle right here is going to be theta 1, and this angle is going to be theta 2. That's standard, right, from refraction. Now I'm going to throw some other angle names. I'm going to name the angle that's out here alpha. And then I'm going to name the angle where the ray is coming down and hits the center line again as beta. And then I'm going to put one more in here. I'm going to look at this angle. We'll call that guy phi, the angle from the center line up to where we actually intersected the curve. Okay, so those are all the angles. And then I'm going to put one more thing in here. We're just going to use this. It's going to go away. But I am going to draw the perpendicular in here. And we'll call that guy H. Okay, so there's the naming scheme for all the stuff from the geometry. All right, well, let's have some fun. We're going to start with Snell's law. All right, so according to Snell's law, we've got n1 sine theta 1 is equal to n2 sine theta 2. Now we're going to do a small angle approximation again, which is going to turn this into n1 theta 1 equals n2 theta 2. Anytime we use the small angle approximation, I'll put a little like red star asterisk thing. Okay, so I'll put that down here. This just means small angle. Because we're going to use this a few times. And I want you to be able to, when you go back and you look at your notes or you watch a video or whatever, you're going to, okay, that's what's going on here.
How small of angles generally do we need?
Small.
Okay.
No. No, I know what you mean. Okay, so okay, that's a hard question to answer because it depends how close you want to be to your actual value. Also realize that when we do this, we're talking radians. So it has to be a small radian number. And small radian numbers happen pretty fast. Because just like 1 radian is 57 degrees. So if you are at, say, 5.7 degrees, that's a 0.1 radian. And on your calculator, if you do sine of 0.1, you'll see that it's not very far off from 0.1. So how small do they need to be? Well, it depends how accurate you want that value to be. I don't like attaching a number to it. That's why I jokingly said small, because it's all relative anyway. And you should know by now that when we do approximations, it's always a, well, how comfortable are you? If you're not comfortable enough, then go smaller. You know what I mean?
Yeah.
But like think about it. Let's just talk about like my glasses, because those are nice little, you know, it's a nice example of something that we can think about. So think about the angles that are going to come from my eye to the glasses. Right now, if we look, like how far is it from the lens to like the back of my eye? Well, it's about that far, right? And then you think about, okay, well, what is the separation of the rays? Well, now you got to get to my pupil. Not the entire color bunches, the black part that's actually allowing light through. Okay, well, now that's like that big. So that big versus that distance. right? And then you cut it in half because it's from the center. What kind of angle is formed from my thumb and my index finger right there with this other index finger being the right angle, right? So that little angle right there, that's pretty small. And so even if we just go with like that example of using curved surfaces and all that, those angles are tiny. And they're small enough that this is going to be okay. Now, take something like, oh, I don't know, a star that's sending light to a telescope. All right, now your telescope, this is your backyard telescope, take half that distance compared to the distance to the star. That's an angle that you can't even really calculate, right? So in most real situations, it's not something we have to worry about because those angles are small. But this is also why things get distorted, right? Like even if you play with just simple magnifying lens, you can get some weird stuff going on with it when the distances aren't good, when weird stuff's happening if you're looking at it from an angle, right? Like, have you ever had that? Well, here's a good example. We were talking about street signs the other day and how they got retro reflection, right? Have you ever noticed that when you drive by a street sign in the day, that it will actually kind of look colored a bit? Like when it's straight ahead of you, it looks white. The speed limit sign looks white. But if you look at it as you're kind of going by and the angles start changing, you'll see it kind of do the rainbow colors.
I have noticed that.
Okay, so you have noticed. So thanks for that, Jacob. I appreciate that I'm not the only one that sees this kind of stuff. Otherwise, maybe I'm just going there. No, but and the reason is now you're at a large angle, right? If this is our street sign, let me pull out some paper down here. So if this is our street sign, when you're coming head on, your angles are small, right? Right? That's a small angle because you're pretty much head on. But as we're driving towards it, and you start looking at it this way, now that's a large angle. Remember, it's large for the perpendicular. And the next thing you know, you start getting diffraction. You start getting the weird effects of the bending. And so all this stuff that we were talking about with small angles goes out the window. So when you're in that situation where you've got the big angles, you'll know because things don't look right. You start getting weird effects, weird images, and it doesn't play by these rules anymore. So, yeah. So to answer your question, how small do they need to be? Well, they need to be small. How small? Well, how good do you want this approximation to be? But for most situations where we use this, the small angles naturally occur. So that was a really long-winded way of saying I'm not going to answer that question. So
That
it's
sounds
like
good to me.
It's the story of my life in physics. I never got, actually tell you guys anything real. Have you noticed that? I just blab until you guys all go, yeah, okay, that sounds good. All right. Anyway, so Snell's law, once we go to the small angle approximation, brings us here. Okay, well, that's great, but we need to start figuring out how these distances are related, right? The object distance versus the image distance. So let's build some other triangles. So now I'm going to use the triangles that involve this guy H. And so this is going to be those that involve the angles like alpha and beta and all that. So the alpha, I know that the tangent of alpha is equal to h over the distance from our object to the front of this curve. And so that's going to be dO. Now, something that I definitely want to acknowledge. dO is only to the front of this curve. The h, the vertical, is a little bit behind it. So I guess technically I need a approximately equal. But you guys already know what else I'm going to do, right?
You're gonna put like a dx or something.
Well, I've got this tangent of alpha. I don't want tangent of alpha, so I'm going to use a small angle approximation on that. Since I'm already doing a small angle approximation, that little bit of extra thing doesn't really matter. And honestly, like if this was, say, the curved surface of my eyeglasses, that extra little distance is within the width of my eyeglasses. You're not even going to notice it. So technically, yeah, it's not, but whatever. We're going to go with it. All right, now, what that tells me then, if the tangent of alpha is approximately, or is h over dO, from the small angle approximation, that means that alpha is pretty much h over dO. So let me make my little mark that it was another small angle approximation. Of course, the last pen I pull out of my pocket is the red one, but this was another small angle approximation. All right, well, let's do the same thing for beta. If we look at the tangent of beta, so this big triangle, it's going to be h over the image distance, right, the distance to this guy. So from the small angle approximation, okay. Okay, now I want to do the exact same thing for phi. So the tangent of phi is going to be h over this line, and that's just the radius of the circle. So by the small angle approximation, then phi is going to equal h over big R. So the small angle approximation basically lets you get angles using the trig functions. All right, so hopefully so far so good. But now I want to relate theta 1 and theta 2 to these guys alpha, phi, and beta. All right, so from some geometry, we get that theta 1 that's going to equal alpha plus phi. And here's how you can see that. Look at the triangle that involves alpha and phi. This angle right there is going to be 180 minus alpha plus phi. Right? Because the three have to add up to 180 degrees. Well, if you look at the or this pink, radial line, theta 1 plus that angle has to equal 180. Well, if theta 1 plus that angle equals 180, and then alpha and phi plus that equals 180, theta 1 is equal to alpha plus phi. So just a little geometry there. And then theta 2, if we do some geometry on this guy, you can kind of do the same thing and go, well, theta 2 plus beta plus this angle equals 180. So theta 2 plus beta equals phi. Well, then that means that theta 2 is equal to phi minus beta. So that's not small angle approximation. That's just how geometry works. All right, well, what we're going to do with those, we're going to take those and fire them in here. But at the same time, I'm going to put these guys in for my alpha, my beta, and my phi. Okay, so I'm just going to do that all at once. All right, so what that gives me, I get N1 times H over DO plus H over R. That was my alpha plus phi. That's going to equal N2 times H over R minus H over DI. All right, so we're almost there. The last step is just more algebra. Take this thing. Notice that all the H's can go away, right? There's an H in each piece. I can just divide them. So it turns out that H didn't even matter. And then I'm going to rewrite things. So I get N1 over DO plus N2 over DI, bring that guy over here, is equal to N2 minus N1 over R. And this last piece, that comes from moving the R on the left over to the right. But we're left with this. And because we know that this is the international signal for we're done, let's put a box around that. Because this now is going to tell you where the image is located. So compare that to the one with the mirror. I know it looks way uglier, but it has really similar structure, right? In fact, let me write the one with the mirror right below it again. It was 1 over DO plus 1 over DI equals 2 over R. So if you look at those, they're actually quite similar. Just because refraction is not that different than reflection. I mean, it feels like it's different, but it's not. It's making use of some geometry. But notice what the big difference is between them. What's the big difference here with what we have now with this refractive surface as opposed to the mirror?
The medium in which we're in or looking at.
Yeah, it totally depends on the media, right? What are these two things? And more to the point, what are their indices of refraction? But that should totally make sense, right? If we're going from, from medium A to medium B, that's going to be different than if it's medium C to medium D. It totally matters what we're going between. So the fact that those show up in that equation, A, should not surprise you, and B, should actually make you feel better about that equation. Yeah, no, it should matter what those things are made out of, right? But other than that, you see that it still depends on the radius of the curvature. Again, makes sense. But this is what's happening when we go now through a refractive surface in terms of location of our image. So just like that one where we were looking at, you know, our image reflected in the Christmas ornament, it's the same kind of thing. If we know where our object is, we know how the curving of the surface is, and we know what the two different media are, we can still calculate where that image is located.
And this equation takes care of all shapes of surfaces, right? Like-
Yeah. Yep. No, we're gonna have to do the same thing where we define positive R versus negative R, positive DI versus negative DI, right? Like, but yeah, it doesn't matter what the curvature, and it actually also works if it's flat, right? Like, think about if it's flat. That was what we derived the first time. And if it's flat, that means the radius of curvature is infinity. Dividing by infinity makes that side 0. And then you see that once you solve for DO or DI, it's going to be the ratio of the other two, of the ends, times the other one, which is exactly what we found. So yeah, no, it's perfect for any kind of surface, curved or otherwise, convex or concave. Well, that's the one that will always work. Okay, but I do need to talk about sign conventions here, because unfortunately, this is different than the mirror. Okay, so first of all, take a look at this image. This guy over there. Is that real or virtual?
It's real.
It is real, because this orange thing is the light ray that went through that point. Okay, so unlike with the mirror, the fact that this image is on the other side of the surface keeps it real, actually. Okay, so here's something that we're going to have to be a little bit careful about now. So here's the sign convention. And I'm going to put here for refractive surfaces, because we're refracting now, not reflecting. All right, so first of all, DI. This is now positive if on the other side. All right, or behind, for kind of like how we talked about it with reflective surfaces. That's the exact opposite of what it was for mirrors. But it has to be this way if we're going to say real means positive. That's like the defining everything when it comes to sign convention, is real is treated as a positive number. Okay, so it's going to end up being negative if on the same side. And that can happen. That can totally happen. Obviously not with how our rays are going with it bending, but you can imagine if we were going to a smaller end value, now we would have bent away, and that never would have actually, that ray never would have intersected the central line, and we would have had to backtrack to some point here. And in fact, think about the example that we did with just the flat, the straight surface. That was one where the image location was on the same side as the object, then it was virtual, right? And that will play out actually with this equation in terms of the sign. So that's the deal with DI. And then with R is a little bit different as well. This is going to be positive if it's convex, and negative if concave. So that's the reverse as well, right? That's reversed as well. So again, this means that the center is behind, or center is on other side. So I'm going to apologize for this, even though it's not my fault, even though it's just, I mean, it's the way that optics was defined and built. Everything works out as long as you follow the sign convention. It's just weird that it switched for these refractive surfaces as opposed to reflective surfaces. But like I said, it all comes from real means positive. Virtual means negative. And if you use that as the overriding everything, it forces this kind of convention for refractive surface. All right, so let's just talk moral of the story real quick. Good news, bad news, right? And it's pretty much all good news. The good news is now we got formulas. We've got formulas that show the relationships between image and object distances for these curved surfaces, which means we don't have to measure anymore. And it allows us to get numbers for things that we can't even measure, right? Like, how can you actually get into this, lens and measure where that image is? You can't physically do that, but that's okay because we got formulas that will do it for us. I think really the only bad news to this is that we are restricted to small angles. We have to have small angles, whatever we want to define small to mean. But as long as we're in small angles, dude, we're good to go. We're totally. All right, so any questions about this guy, this equation, where it came from? Hopefully the derivation made sense. But like I said, if you were to take that, let R equal infinity, and then solve for your DI or your DI for a flat surface, you're going to see we get exactly the same formula that we got when we developed it independently. All right, well, I think this is good enough for today. I know we have a little bit of time left, but I think we'll call it good. So just so you guys know, on Thursday, couple of things. Don't forget to finish the homework from the first set that's due tonight, tonight at midnight. So get that uploaded. We're also going to have a quiz next time, and that quiz is going to be on the first chapter, chapter 1. So it's not going to be any of this geometric stuff, but it's going to be the other things like using Snell's law, finding angles of reflection, stuff like that. So we'll have a quiz that will open up at the start of class. Again, you got, I think I said it was 40 minutes. So we'll actually start, instead of at 4, we'll start at 4:40. But you guys know the drill. It was like that when we've had calculus and stuff. You've had calc and stuff before. So, but that's going to happen on Thursday. All right. And then what we're going to talk about on Thursday is more of this. We'll actually go to okay, well, what about when you have thin lenses? And then we'll be able to put them together and talk about things like telescopes and microscopes and why they do what they do. All right. So with that, I'm going to wish you all a wonderful couple of days. And I will see you all on Thursday. Actually, that's not true. I'll see you all tomorrow for Dippy Keys. All right. So have a good one.